4-point function in that language. Then they could have looked into this correlator, things like this, and so on. Okay? And you can do, what we worked with this example was this case, this associativity condition. Okay? The OPE, they want your channel, and in this channel here, for this correlator, in this realizing model, led us to this. It leads to some conclusions about the possible range of scaling dimensions and so on, but it's not the whole story. Then you can look to this correlation, and play the same game, you obtain another bootstrap equation here that you can solve by the same strategy in principle. But the nice thing to about classifying these operators in all possible symmetries present is that because you can start at least to ruling out some operators from the OP of the others. Okay? Because I believe that in this OP that we worked out, there cannot be any odd spin operator. Be it primary, be it descendant, be it whatever, relevant. Because then you delete contradictions. Okay? There's some more formal result that you could prove. This has to do with in this case, to O symmetry, exchange operators. But yeah, there are more maybe formal considerations that you take into account. But usually the idea is if you take the bootstrap equation, okay, identify your primaries, your relevant primaries, and maybe the first few relevant primaries. Classify them according to all the symmetries you have, and by primaries I mean the scalar primaries and the spinning primaries as well. If you have any discrete symmetry, you can classify them accordingly too, and then take these correlators and look for the bootstrap equation they furnish, and to actually solve numerically the bootstrap equation, or to find some set solution inside for some given range, just get some values for the scale dimension based on unitarity bounds. If you're interested in unitary series only, and so on, and then do some nice plots to show the results, and so on. The one thing they do, they study this at increasingly more complicated, take into account more terms here. I guess the first estimate they take just an approximate version of that geometric function with some expansion, and they just take into account scalar operators in the OPE, and they obtain, but like a hydra, you obtain some region like this. They start improving by using the exact expression, I guess, and take into account more operators in the expansion. Then you see that this region starts to shrink, and it shrinks a lot. So that's what I mean by powerful constraints. Maybe even unexpectedly powerful. And are there any more questions? I just want to give you an idea how this is a line of research, and I just want to give you an idea how it works. It is the way I think it works. I don't do research. My knowledge in this is limited, but I believe it is pretty much along this line. Okay, this general strategies like that. If you want anything more specific, you can look at this reference that I'm about to write here. Those lecture notes that I gave you in the first class, by the end of them, they all discuss conformal bootstrap. They take some of these examples. They typically always discuss this, the classic example. They'll discuss this a bit more analytically than I did. They'll work out these geometric functions a little bit more explicitly, but then they will discuss the numerical methods a bit more than I can discuss. And then if you want it to go even deeper into that, you should look at the literature. I'm just going to give you the main papers here. Okay. This of the Ising model is on FTH 03 6064. It's by Duffing appears here after everyone else because it's Simon Duffing, but too lazy to write Simon Duffing, so I just write Duffing. And it is titled Solving the 3D model. With the conformal bootstrap. There is another one that they explain a little bit better, how this process of bounding the scaling dimension operators works. This one came out in 2012.
Yes, it's good.
Oh yeah. Okay. This one came out much before it came out. Not much before. This one came out in 2008. Oh, 08, 07, 04. By Tadzi, Rishkov, and it is titled Bounding Scalar Operator Dimensions. In four-dimensional safety. I guess in this one they explain that geometric interpretation of the vectors a little bit better. This one was 2008 first. And those two about the conformal partials, if anyone's interested in the actual many pages of hard computations, analytic computations. There are two works, but so this is two. So both papers are by Dolan and Osborne. They are. Okay, they are both FTH. The first one is kind of old, so like it came out in 2003. So 03, 09, 0. It is titled Conformal Partial Waves and the OPE. Okay, the title is not abbreviated like this. Get it? And the other one came out in 2011, a bit more recent. 1108, 6194. And the title is Conformal Partial Waves for the mathematical results. Okay, so long before this conformal bootstrap program began, around 2008, by this paper, I guess, and even more so after this managed to solve the 3D model in 2012. The fact that those conformal partial waves were given by hypergeometric functions or recursion relations in all dimensions was already known in this paper in 2003. Okay. And inside the reference of this paper, you can find many more references. I guess there is another one that followed this one. Something like, it has a similar title, where they basically, I guess they study the same problem, but they managed to improve the results. the techniques and so on. Okay? I guess by the same people. I guess with these two references, if you're into conformal bootstrap, these two references maybe a good starting point together with the lecture notes. Okay. And inside them you can find many more. Okay. So any questions? No? Because now we will just end this discussion and then we'll take some steps back and we'll discuss the word identities in conformal field theory. This is something I could have discussed like by lecture 3 or something like that. We just need the conformal algebra, the structure of the conformal algebra. And then we will discuss the average moment of tensor, and then we'll be able to access the question of scaling versus conformal invariance better by studying the average moment of tensor. And I may also give you the structure of the correlators for spinning fields, including spinning fields. Okay, they have pretty much the same kind of power law behavior, but they have some, of course, tensor structure in the numerator. Okay, so you may need to work that out a bit. That's it. You'll be a completely different. You'll be like a clean slate. Okay? Just stop here, presenting. Just go back to lecture 2, and then continue from there. Okay. So, and next lecture is 2 weeks from now because there is a holiday. The next term.